Hello learners, I am Dr. Akshay Sarkar, an assistant professor of chemistry from the Ganpat Parshakar College of Education, Goa. I welcome you all today to this chemistry MCQ solver course. In today's session, we are going to see some commonly asked MCQs based on electrochemistry. Let us look at the first problem. The resistance of 0.01 normal NaCl solution at 298 Kelvin is 200 ohms. Cell constant of the conductivity cell is unity. Calculate the equivalent conductance. The options given are 500, 850, 700 and 980 per ohm per centimeter per equivalent. To solve this problem, we have to know how specific conductance is related to the cell constant. The formula is K equals to 1 upon R into the cell constant, which is 1 divided by 200 into 1 centimeter inverse. This gives us a value of 5 into 10 raised to minus 3 per ohm per centimeter. Next, to calculate the equivalent conductance, we have to use lambda m equals K into 1000 divided by normality, which comes to 5 into 10 raised to minus 3 into 1000 divided by 0.01. Thus, we get the answer as 5 into 10 raised to 2 per ohm per centimeter per equivalent. Thus, option A is the answer. Let us look at another problem. A base has a dissociation constant equal to 1.8 into 10 raised to minus 5 at 298 Kelvin. What is its degree of dissociation at a concentration of 0.1 normal at the same temperature? The options are 0.0875, 0.0652, 0.0524 and 0.0134. This problem is based on the Oswald dilution law. It relates the dissociation constant of a weak acid with its degree of dissociation and concentration. Suppose the base is BOH and alpha is its degree of dissociation. Then we have BOH dissociating into B plus OH minus. The initial concentration values will be 0.1 molar for the reactants and 0 for the products. Concentration in equilibrium will be 0.1 into 1 minus alpha for the reactant side and 0.1 alpha for both the reactants separately. The dissociation constant will be equal to the sum of the product of concentration terms of the reactants divided by the concentration of the product. If we substitute the value of Kd, that is 1.8 into 10 raised to minus 5 and 0.1 alpha for B plus and OH minus and 0.1 into 1 minus alpha for the concentration of BOH, we get a value of alpha that is equal to 0.0134. Thus, the answer is option D. Let us look at the next problem. The equivalent conductance of a very dilute solution of sodium nitrate at 18 degrees C is 105.2 per ohm centimeter square. If the ionic conductance of NO3 minus ion in the solution is 61.7 per ohm centimeter square, calculate the transport number of Na plus ions in the solution. The options are 0.414, 0.145, 0.852 and 0.631. This problem is based on ionic conductance. Given that the equivalent conductance of NaNO3 is 105.2 per ohm centimeter square, and using the formula lambda NO3 minus equals to neta of NO3 minus into lambda naught NaNO3, wherein the lambda NO3 minus is the ionic conductance of NO3 minus and neta stands for the transport number. Thus, the transport number of NO3 minus comes to 0.586, and if we subtract it from 1, we get a transport number for its counterpart, that is Na plus ions. Thus, option A is the answer. Next, let us look at another problem. What is the standard EMF of a cell which involves the following cell reaction? Zn plus 2Ag plus giving Zn2 plus 2Ag. Given that the E0 values of the zinc system equals 0.76 volt and the E0 values of the silver system is given as negative 0.8 volt. The options are 1.42, 2.51, 2.98 and 1.56. This problem is based on calculating the standard EMF. As the oxidation takes place at the zinc electrode and reduction at the silver electrode, by convention the cell may be represented as Zn/Zn2 plus separated by Ag plus/Ag. Standard EMF of the cell, that is E naught of the cell, is given as standard reduction potential of right hand side minus the standard reduction potential of left hand side. If we substitute the values of 0.8 and negative 0.76 in the above formula, we get answer of 1.56. Thus we can say that option D is the correct answer. Let us see the next problem. Calculate the EMF of a zinc silver cell at 30 degrees C when activity of Zn2 plus ions is 0.5 and activity of silver plus ions is 10. Standard reduction potential at 30 degrees C are values for silver electrode equals 0.799 volt and the zinc electrode is given as negative 0.76 volt. The options are 2.851, 3.451, 1.628 and 8.516. This problem is based on the Nernst equation. Based on the reduction potential, it can be concluded that reduction takes place at the silver electrode and oxidation at the zinc electrode. Zn plus 2Ag plus giving Zn2 plus 2Ag. Here n is equal to 2. The cell may be represented by Zn/Zn2 plus separated by Ag plus/Ag. Standard EMF of cell is given by E naught equals to E naught of the silver system minus E naught of the zinc system, which gives us a value of 1.559 volt. By Nernst equation, the EMF of the cell is given by E equals to E naught minus RT upon NF ln the activity of Zn2 plus divided by the square of the activities of silver plus. If we substitute the corresponding values, we get an answer of 1.628 volt. Thus, option C is the answer. Next, let us see the next problem. Calculate the EMF of the below cell at 25 degrees C. Mg giving Mg2 plus at a concentration of 0.01 molar plus 2 electrons. The E naught value for this cell is given as 0.34 volt. Tin 2 plus at a concentration of 0.1 molar plus 2 electrons giving tin. The E naught value is given as negative 0.136 volts. The options are 1.525, 3.547, 2.234 and 8.251. This problem is based on the Nernst equation. The cell may be represented as Mg/Mg2 plus separated by tin2 plus /tin. The standard EMF of the cell is given as E naught equals to minus 0.136 plus 0.34 volts, which gives us a value of 2.204 volt. The overall reaction is magnesium plus Sn2 plus giving Mg2 plus Sn. If you use the formula E equals to E naught minus 0.0591 upon 2 log of the activities of Mg2 plus divided by tin2 plus, we get the answer of 2.234 volt. Thus, option C is the answer. Let us see another problem. Calculate the EMF of the following concentration cell at 25 degrees C. Copper/copper sulfate given M equals 0.02 and gamma equals 0.32 separated by copper sulfate, wherein M is given as 0.2 and gamma as 0.11 separated by copper. The options are 0.0158, 0.0365, 0.0525 and 0.0740 volt. This problem is based on concentration cells. If you use the formula E equals to 0.591 divided by N into log of A2 divided by A1, wherein A2 stands for M2 gamma 2 and A1 stands for M1 gamma 1. Substituting the values, we get the answer which comes to 0.02955 into 0.5363, which gives us a final value of 0.0158 volt. Thus, option A is the correct answer. Let us see one last problem. Consider the cell platinum/H2
at 1 atmosphere separated by H1 x molar separated by KCl at a concentration of 0.1 molar separated by Hg2Cl2/Hg, which stands for calomel electrode. If the EMF of the cell is 0.5 volt at 25 degrees C, what would be the pH of the x molar acidic solution? Given the electrode potential of calomel electrode is 0.281 volt, the options are 2.25, 3.71, 8.65 and 7.25. This problem is based on calculation of pH. EMF of the cell, that is E naught of the cell, is given as electrode potential of right hand side electrode minus electrode potential of the left hand side electrode. In this case, the right hand side will be the calomel and the left hand side will be the hydrogen electrode. If we substitute the values, we get E for hydrogen as equal to E of calomel minus E of cell, which comes to 0.0591 minus log of H plus, which gives us a value of 0.0591 pH, okay, which is an elaborated expansion of the log of H plus, which stands for pH. If you use the formula, pH equals to E of cell minus E of the reference, that is the calomel, divided by 0.0591, and if we substitute the values, we get a final answer of 3.71. Thus, option B is the correct answer. Thank you all for your attention.